So assignment 3 will be due on Friday, 2 weeks from last Friday. So that was the 12th, so the 26th. 2/26, and then exam 1 on chapters 1, 2, and 3 will be on Monday, the following Monday, so that's March 1st. Okay.
I think that's spring break.
Oh, was it spring break already? Oh boy. Should check that. So spring. Oh, it is. Okay. Oh boy. I hate to have it. I hate to delay it a week after that. Oh my goodness. Well, I guess there's no helping it. So it's going to be on Monday the 8th. We just don't have enough time to get um, to this material unless people would rather have the assignment due on Thursday and have the exam on Friday. What do y'all think? We could have the assignment due on Thursday, and then on Friday we have the exam. You guys want to do it that way, or would you rather have it due on Friday?
Would we be able to?
Sorry.
Would we be able to get our grades back on it before we take the exam?
Yeah, I should be able to do that. Yeah, I mean, it's not a whole lot of time there. Um, is anybody in favor of doing the exam on Friday the 26th as opposed to Monday the 8th? So, I mean, that means you got to think about it over spring break.
I would rather do it before, but
Anyone else? Other preference?
I like the idea of March the 8th because if we just get our grade back for assignment 3, it's kind of hard to
Digest everything.
improve from our last assignment and then do the exam in 2 days later.
Yeah, I agree with that.
Yeah, I'd agree with that.
So, I mean, while y'all are on the beach in Daytona or Padre Island or whatever it is these days, you want to think about set theory? Of course, probably nobody's going anywhere these days, but so I have 2 people for the 8th and 1 person for the Friday. Anybody else want to chime in?
Before.
4.
The 8th works better for me because I have 4 other exams the
Okay,
week before spring break.
The
8th works better for you.
All right, okay. So it sounds like the 8th. Did anybody vote twice? Did I just hear everyone? Did anybody? Okay. All right, so it's going to be the 8th. There's not a lot of helping it, but we'll have more time to discuss the material. Yeah, okay. All right, so let's close that. All right, so let's just get back into the lecture. Did I close it? I closed it, didn't I? And let's finish this so we can get into doing proofs. Oh, I'm so confused today. All right. So we were talking about operations on sets. Okay, so we're going through a lot of definitions. So you got to know the definitions. Everything starts from the definitions. If you don't know the definitions, you can't do proofs. Okay, everything stems from the definitions. That's the beginning of the discussion. Okay, so we're defining a lot of things. So you have to slog through it and understand those definitions. So given two sets A and B, the intersection A cap B like that, and that looks like an and, right? And it's defined with and. So it's a rounded cap rather than a sharp wedge. So it's the set of all x for x in where x is in A and x is in B. So it looks like this. So the overlap of two sets. So these two sets here, they overlap in 1 and 3. These two sets, they don't overlap. So it's empty set. When A intersection B is empty, we say they're disjoint. Sometimes people say mutually exclusive. That's kind of like a term used in probability and statistics a lot. Union. Given two sets A and B, A union B, it's the set of all x such that x is in A or x is in B. So the union, which is this U without the serif there, it's defined, it's a similar symbol to the or, and it's defined using or. So, for example, these two sets, their union is just every element you see, right, in this set or that set. This one, the union is here. Notice the following, which is kind of interesting. A union, the empty set, is just A. A union A is A. Looks like identity and idempotent, doesn't it? Well, it's exactly that, actually. That's exactly what you call it. Similarly, the intersection, you have the same kind of thing. A intersection A is just A. And A intersection, the empty set, well, not the same thing, but similar stuff as well. What's A intersection empty set? That is, what's the overlap of A in the empty set?
The empty set?
Empty set again. Right? The set of all x, where x is in A and x is in the empty set. Well, there's nothing in the empty set, so it's just empty. All right. Complementation. So this one's got a bit of a twist to it. Given a set A, which is a subset of some like sort of universal set U. So in order to define complementation, you have to have some universe in which you're working in. You have to have an overall universal set where that set contains all the other sets that you're discussing. Okay, and that's easy to you always have such a thing. But I mean, you can change that thing. I mean, it could be this, it could be that, it could be something else, and the definition of the complement changes. So you have to be aware of what this is in order to talk about the complement. So given a subset of a universal set, a complement, notice that's like negation there, right? It's the set of all x such that x is not in A. So in a diagrammatic picture, right, here's your universal set, and here's A, and the complement of A is just all the stuff that's outside of that. Right, so I mean, depending on what U is, that complement changes. So sometimes it's important what U is specifically, other times it's not. Just one needs to be aware that if you're going to talk about it specifically, you need to know what it is. So for example, equal to the set of digits base 10, and A is the set of even ones, 0, 2, 4, 6, 8. All right, then a complement is what? What's a complement? What's a complement in this case? Everything.
1, 3, 5, 7.
The odd ones, yeah. 1, 3, 5, 7, 9. Right. So it's exactly the stuff that's not there. Right. So a similar sort of example. If u is equal to the whole set of integers and a is equal to the set of all 2k plus 1, such that k is in Z, right? Then, well, what's this? Right, what's this? That's the set of all 2k plus 1, such that k is in Z. What are 2k plus 1? What is that? That's
All the odds.
Yeah, all odds. So the complement is the set of all evens, right? Which is going to look like what? The set of all. How do you define even numbers? These are odds, right? It's always an even plus 1. So the evens are everything that's divisible by 2. So it's all what?
K divided by 2 such that K is an element of Z.
2k, such that k is an element of Z. When you divide even by 2, it could be odd, right? Like 6 over 2 is 3. But when you say divisible by 2, you mean like a multiple of 2. Right? So that's complementation. And now, after complementation, we come to this thing called set subtraction. Now, this isn't exactly like arithmetic subtraction. So, given two sets, A and B, right, A minus B, it's the set of all X such that X is an element of A and X is not an element of B. The set of all X such that X is in A and X is not in B. So in a Venn diagram, it looks like this. So here's A, here's B. Make it overlap a little bit more. So everything that's in A but not in B. So it's this bit of A. Right? This missing bit for A, that's the stuff that's in A and in B. That's the intersection of A and B. Right here. So that's what you take away. Right? So for example, before that, note, okay, because right, A minus B is defined by conjunction, right, is defined by conjunction, it's actually an intersection of sets. So not only is it, set, definable this way as subtraction, it's something different than intersection, but because it's defined with this, it must be somehow written as intersection as well, because it's defined with conjunction, and conjunction gives you set intersection. In this case, what? All right, A minus B is actually what? It's the intersection of what two sets? The set of all x, such that x is in A, so that's A, and x is not in B. X is not in B is what? What set is the set of x, such that x is not in B?
Was it the complement of B?
Yeah, so this is actually A intersection B complement. Right, and you can write it, you can rewrite it, here's a universal set like this, right? This is equal to the set of all x such that x is in A and x is not in B. Right, but x not in B means the same thing as x is in B complement. Right, x is in B complement, so in this case we just have that this is A intersection B complement. So you can define it, you can think of it in two different ways, as A minus B or A intersection B complement. So for example, if I had something like this, if A is equal to 0, 1, 2, 3, 4, 5, and B is equal to 3, 4, 5, 6, 7, 8, 9, right? What is A minus B? A minus B is going to be what? It's everything that's in A, but not in B. Which things of A are in B? Well, it's those. Right? Those are the things that are in A and B. That's the intersection of A and B. So in this case, A minus B is what? Right? Take A and throw out everything that's in B. And I'm left over with what?
0, 1, 2.
0, 1, 2. Notice the 6, 7, 8, 9 have no bearing on A minus B. Okay, so it's not quite like set subtraction, like that what was here suddenly is reflected here. It's not. All right. And what about this? How about B minus A? In this case, is going to be what?
6, 7, 8, 9.
6, 7, 8, 9. All right. Also, note the following. A minus A intersection B. Well, A was 0, 1, 2, 3, 4, 5. Minus A intersection B, well, that was just 3, 4, 5. And what's left over is 0, 1, 2, which is the same as A minus B. So A minus A intersection B, in this case, is the same as A minus B. That's going to be true in general. It's not too hard to see that. But we'll go over why, formal proofs of why that's so. With just a little preview of it right there. Okay. So since we've defined these, so these are the set operations that we have. There's more. I'll give you one more. Symmetric difference. So with symmetric difference, it's A, and then you've got this delta. A delta B, or asymmetric difference B, it's the set of all X such that X is an element of A union B, and X is not an element of A intersection B. Which happens to be the same as the set of all X such that X is in A minus B, or X is an element of B minus A. Right? This is equal to, if you want to write it differently, A union B minus A intersection B. This is A minus B union B minus A. It's not necessarily immediately apparent that they're the same. But again, we'll go over a proof of why. These are all nice examples, of getting started on how to do some kinds of proofs just involving these set operations. But in a Venn diagram, it looks like this. Copy that one over here. We're not going to use this one very much, but for what it's worth, here it is. Depending on what area of mathematics you're sort of looking at, symmetric difference gets used more or less. In combinatorics, it tends to be used a lot, actually. And sometimes it's not written with that triangle; it's written with just a plus. Sometimes it's called addition of sets. So, and it's this. It's A union B minus the intersection part. And sometimes it's written. So some folks use A plus B to mean A triangle B. Depends. All right. A connection with propositional logic. Since these set operations are defined using propositional logic, the tautological equivalences using and, or, and complement translate directly to the following identities on sets. Not the implication, because implication is used to define subset, the subset relation. The subset relation isn't an operation on sets, right? And an operation is something you do to two sets or to one set to transform it into something else, right? So intersection takes two sets and gives you something else, a third set. Union takes two sets, gives you a third set. Like addition, subtraction, multiplication, division. You take two numbers, put them together, and you get something else. You also have this unary operator. You take one set and you take its complement, and you get something else. Right? In propositional logic, you also have that. Right? You have operations on the values true and false, and then you can take the conjunctions of trues and falses, disjunctions and negations of trues and falses. But you also have this operation called implication in propositional logic, but it's not an operation in set theory. So propositional logic is a little bit more general a concept than this set theory stuff. In some sense, it's a little bit more general. But here we still get a lot of leverage from that. So we get the following. So let's go back to our notes from chapter 1. And let's look at those tautological equivalences. They are right there. All right, so all the ones that don't use implications, they're going to translate here. So not this one, not implication, not contrapositive, not double implication. Not implication, well, you know, it uses implication, but it turns it into a disjunction. So whereas implication isn't something that defines an operation on sets, it can be translated into something that does. So in that sense, you do have implication in set theory. But, you know, these translate directly. Associativity, commutativity, double negation. So we have associativity. Associativity is that A intersection B intersection C is equal to A intersection B intersection C, because conjunction is associative and intersection is conjunction. Intersection must be associative. Very simple. Same thing with union. A union B union C is equal to A union B union C. Commutativity. A union, well, we'll do intersection first. A intersection B is equal to B intersection A, because conjunction is commutative and intersection is defined directly using conjunction. Intersection must therefore be commutative. Same thing with union. Distribution. A union B intersection C becomes A union B intersection A union C. So I mean, it's the same stuff as before, just the context and the symbols are a little bit different. And then the opposite one, A intersection B union C, is A intersection B union A intersection C. Other ones, what else? What other ones are going to apply here? So we got associativity, commutativity, distribution. How about double negation? Is that going to work? Is it defined just with unions, intersections, and complements? Yeah, it is. So that one works too, double negation. Double negation. That A complement is just A. What next? Important one. Definitely an important one.
De Morgan.
De Morgan, yeah. De Morgan's totally an important one. De Morgan's laws. A intersection B complement is A complement union B complement. A union B complement is A complement intersection B complement. What did I do? There it is. Right. How would we do complementation? How can we, there's no 0 and 1 in set theory. What takes the place of 0 and 1, do you think? The 0 is going to be the empty set, and the 1 is going to be your universal set. All right, so complementation, right, U equals a universal set. And that is that A intersection A complement is empty. A union A complement is going to be that universal set. Identity, again, U equals a universal set. You know, which can change depending on the context, but you know, as long as you have such a thing that's defined, then you can do these things. So identity is that A intersection A intersection the universal set is A, and A union the empty set is A. Annihilation, again, U is a universal set. A intersection the empty set is the empty set. And A union, the universal set, is the universal set. And the last one is idempotent. A intersection A is A union A is A. So all of that stuff from propositional logic, you know, it just gives you these identities on sets for free. Okay, so you know the things that dealt strictly with implication, they're not really there. Okay, although you can think of implication as A intersection B complement. Or sorry, that's the negation. A complement union B. All right. Although that can be kind of awkward sometimes, but you know. So, for example, so let's use these set identities to prove that. Now I want to make sure I don't. I had a. Here's assignment 3. I had a list of examples I wanted to do, and for some reason I lost it. So I want to make sure I don't do what's in the assignment 3. 2, 3. Yeah, okay, it's not there. So using these sets identities to prove that A minus B is equal to A minus, let me do it this way, A minus A intersection B is equal to A minus B. So, you know, I did an example in which this was true. I had two sets, A and B, and A minus A intersection B was the same as A minus B. But that's true in general. That's going to be true in general. Okay? So, how can we start this? We start on the left and we work our way over to the right. Notice that none of these set identities here use subtraction. Right? There's no set subtraction in here anywhere. It's just unions, intersections, and complements. But set subtraction, you know, was definable using intersection and complements rather than, you know, just using this notation. This notation is maybe a little more intuitively clear, but how does one define set subtraction with just intersection? A minus B is the same as A intersection B complement, just by the definition of complement and intersection. They are the same thing, right? This, by definition, is the set of X, where X is in A and X is not in B. But X is not in B mean X is in B complement. So this is the same as the set of x such that x is in A and x is not in B. But by definition, that's, sorry, x is in A and x is in B complement. But by the definition of intersection, it's that. So anytime you really want to talk about subtraction, you want to use these identities, okay, you have to redefine it using intersections. So this becomes what? A minus A intersection B, right, by definition of set subtraction is what?
A intersection parentheses A intersection B complement.
Right. So now by De Morgan, what's this here?
A intersection, parentheses, complement A, union, complement B.
Exactly. Do I need that parentheses there? Well, just as with propositional logic, right, this is not equal to this. You can't mix your ands and ors because there's no operator precedence there. Same thing with intersections and unions. You can't mix the intersections and unions. There's no operator precedence there because there's no operator precedence for ands and ors, conjunctions and disjunctions. So yeah, it's got to be there. By De Morgan's law, this is equal to that. This bit is hanging on to that. So what's going on in the parentheses here, right, is different than what's going on with the conjunction with A. So the conjunction with A stays, but this transforms into that, and those parentheses need to be there. All right, what could I do now? Which one could I use, you think? Which set identity or which propositional logic tautology can I use?
Distribution.
Distribution. Yeah. So this is A intersection, A complement, union, A intersection, B complement. All right, well, what's A intersection, A complement? By complementation. A intersection, A complement. Everything that's in A and not in A. How many elements are both in A and not in A?
It's the empty set.
Just the empty set. Of course, nothing is both in A and not in A. Right? This is, strict logic. True or false. There's no fuzziness here. There's no quantum logic or fuzzy logic. Either it is or it ain't. All right, empty set, union, whatever is what?
Is what it's being union with.
Yeah. By the identity, A union empty is just A. Or whatever union empty is whatever. That's identity. So this is just equal to, let's go over here. Let's see. Oh my gosh, why is it? Complement. Empty set union A intersection B complement, which is equal to, by identity, A intersection B complement, which is what? By definition.
A minus B.
A minus B. right? And that's what we wanted. We want that this is equal to that. So propositional logic, tautologies, there they are again. Let me close this and reopen it. Okay, why don't we try something else like that? Well, let's go on to something else. So that's one way to prove equality of sets. So how about this one? As I was saying earlier, with this symmetric difference. That symmetric difference, you could define it as A union B minus A intersection B, or A minus B union B minus A. Right? Symmetric difference. Right? There's symmetry and there's difference. But they're the same thing. Why don't we give that a shot? Let's try to prove that using these notions of propositional logic. So again, use these set identities to prove that A minus B. So the two ways of defining symmetric difference show that they're actually the same. Show that these are actually the same. So I'm gonna start with this side, I think. And on the homework, here it is. On number 2, let A and B be sets, and using a string of equalities and basic identities concerning sets, prove that A intersection B complement to complement. This is just A intersection B. Okay, so doing the same thing that we were just talking about, in these examples here. This is what I want you to do in number 2. Now, that's not necessarily the best way or the only way to prove that two sets are equal. If you can do it that way, it's often the most efficient way to do it. But there's another way to do it that's more general that we'll talk about here in number 3. But we'll get to that later. So number 2 is just like these examples that we're doing, which is just like stuff that you did on assignment 1 anyway. So I'll start with this one here. So starting with A union B minus A intersection B. All right, by definition of set subtraction, this is A union B intersection A intersection B complement, right? And then by De Morgan, right, this is A union B intersection A complement union B complement. Now, I would like to use distribution here, but unfortunately I can't, because right, it sort of looks like this is union of A and B, that's intersection, and this is union of, well, it's not A and B, it's A complement and B complement. So I can't use distribution in the way I was just thinking about it. So what I'm going to do is I'm going to distribute this set over these two. So by distribution, so pay attention to how I do this. I'm going to think of this as just one item, and I'm going to distribute it here and here. So I'm saying that this is A union B, that one item, intersection A complement. union A union B intersection B complement. Now I'm going to do distribution again. Right, so it's kind of like foiling. So I'm going to do we're doing distribution 4 times. Right, I just sort of, it's like doing FOIL, I guess, distributing a binomial over a binomial. Right, like that FOIL mnemonic, but so distribution times 2 here. So this is going to be A intersection A complement A intersection A complement union A intersection B. But now it's just going to be a bunch of unions, so I can leave all that out. A intersection B complement union B intersection B complement. Right? It's just 3 unions. So I actually don't need those parentheses there now. Well, what about these? This one and this one. What can I do with those? I think I'm missing a complement somewhere. This is a complement.
They're both empty set.
Yeah, those are both empty sets. So this is empty union A complement intersection B union A intersection B complement. Union empty set. Right? And that was complementation. And then by identity, right? Then by identity, what do I have? Right? This is empty set union whatever. And again, empty set union whatever. So yeah, just these 2 terms right here.
Yeah.
So A complement intersection B union A intersection B complement. What happened? Something didn't work out the way I thought it was gonna. Oh, wait a minute. I'm starting with this. And I'm working my way to that. A intersection, so that's this. Oh, right, I'm working my way over to this one. Right, and then by definition, what is this? B intersection A well, let's do commutativity so you can see what I'm talking about. All right, this is B, well, let's write A intersection B complement union B intersection A complement. And so by definition, these are what? A intersection B complement is what? This one.
It's A minus B.
Yeah, it's A minus B. Definition of set subtraction, union. And this one is B minus A. Right? That's what we wanted. Right? So those 2 ways of defining set subtraction, or sorry, symmetric difference, right? Using set subtraction and union, or just union intersection set subtraction like that, those 2 ways of defining it are actually the same thing. Right? It's not the simplest, string of operations, but there it is. Okay, so just in the last minute here, so a more general way of showing two sets are equal. So two sets, so given two sets A and B, A is equal to B if and only if, well, A is contained in B and B is contained in A. So the subset thing is a relation, right? Talking about one set being a subset of the other is a relation. It's not an operation on two sets. So, you know, when we're using propositional logic, we're just using operations on two sets. But if you want to show, you know, more generally that two sets are equal, right, you can just do this. Show that A is a subset of B and B is a subset of A. Right? Every element in A is an element of B, and every element of B is an element of A. So the only possibility is that, you know, they're the exact same sets. So how you do that, this is going to be our first foray into verbal proofs right here. And we'll do that next time. Okay? So please, everybody, make sure we come to class because we're going to start, you know, talking about things, and we need to be present and asking questions and stuff. But in the meantime, why don't you do these two examples on your own? Get started on the homework. So you have enough info to do 1 and 2 now, and maybe even number 3. Okay? You have enough info to do 1, 2, and maybe 3. So why don't you get started on those and go over these examples on your own, okay? And we'll see you next time. All right, everybody, have a great afternoon. See you later.